Assalamualaikum, my name is FIKRI bin KAMARUDDIN and I will be presenting my project entitled The Effect of Fiber and Nanomaterials on Mechanical Strength of Polylactic Blend. For the introduction, I will be covering on these three aspects. The first one by Chandran, the investigation of new manufacturing technique like FDM shows potential for competing with conventional methods in terms of ease and use and minimum human interface in the process. Second is from Aguero, stated the use of polymers as a matrix has improved the mechanical properties of biocomposites reinforced with natural fibers. The matrix material is the next noticeable and vital ingredient after the fibers. An excellent matrix material transfers load to the fibers and holds them together, improving the composite mechanical properties. Lastly is by Lowell found out numerous research groups have reported on the inclusion of graphene into nanocomposites and the resulting improvements in the composite's mechanical strength and electrical conductivity. For the problem statement, Farah et al. 2016 reported that PLA is eco-friendly, biocompatible, good thermal processability, and low cost. However, it has brittle behavior and degradation over a period of time, says Chow 2020. Thus, to overcome this limitation, this research aims to increase the potential of PLA. It has been discovered from previous studies. Hybridization involves a combination of fillers and natural fibers that result in increased mechanical properties of the composite, said Han 2005. Young's modulus and impermeability of the PLA matrix were enhanced by its blending with graphene oxide and graphene nanosheets, said Pinto et al. 2013. This research consists of three objectives, which is first, to identify the tensile strength of PLA additive materials, focusing on natural fiber and nanographene. Second, to analyze the morphology of surface fracture of tensile break specimen for each composition. Third, to determine the effect of distribution and adhesion of fiber and nanomaterials in PLA blend towards mechanical strength of each blends. This part shows the scope of project where we want to carry out the blending process of the polylactic acid separately with fiber cockpit and graphene nanomaterials at specified composition, and to analyze the mechanical property of each blend composition through tensile strength by using the Shimadzu AGSX, and observe the fracture surface morphology of tensile break specimen for each composition, and lastly, to analyze the interaction and the effect of distribution between nanomaterial with PLA and biocomposite through the SEM analysis. This is the literature review of previous research. This part covers all the methods and processes used to perform this project. Methodology. Figure 3 shows the process flow of the project, where the critical part starts at the preparation of sample, testing and analysis until determining the tensile strength of the blends. Then the figure 3.2 shows the raw materials involved in this research. Next is 3.1, which is sample preparation for tensile strength and morphology analysis. In the table 3.1.1 shows the formulation of PLA fiber consists of 5 formulation A, B, C, D, and E and the amount of fiber content. Table 3.1.2 shows the formulation of PLA graphene consists of 3 formulation A, B, and C and the amount of graphene and compatibilizer agent TP01 content. The process started with calculating the weight percent of each materials and determine the amount needed for each sample. Next, the PLA filament was crushed into granule size. And third, the raw materials were mixed by the compounder machine. The fourth step is blending process using Brabender machine with according to the parameters table below. Then the blend samples were crushed to be fed into the tensile mold. Then the samples go through hot press machine with according to the parameters table shown above. Next, the tensile testing was conducted using the Shimadzu AGSX machine. For 3.2, which is sample preparation for SEM analysis, the fracture part of the tensile samples were then coated using sputter coat device. Lastly, the fracture surface images was captured using Zeiss Evo VP SEM at a magnification power of 200, 500 and 2000. So for the result and discussion, table 1 shows the max force and max stress of PLA fiber blend from tensile strength test. Addition of fiber up to 50% into PLA blend reduced the mechanical strength of the blend except for 20% of fiber. For the 80-20% of PLA blend, revealed a small increase about 2.35% in tensile strength. However, a further increase of 30% and 50% of fiber in the blend shows a large significant decrease in tensile strength, about 21.16% and 25.32% respectively. In the case of PLA graphene blend, Table 2 shows a significant reduction of tensile strength of the blend nanocomposite. For the addition of 0.25% graphene in the blend, results to decreasing in tensile strength up to 36.78%. However, further increase of graphene to 0.5% reduces the tensile strength by 18.12%, which is half of the value of tensile strength in 0.25 graphene in PLA blend. But a further increase of 0.75 graphene in the blend reveals a small significant decrease in strength of about 3% compared to 0.5% graphene blends. Okay, this part shows the SEM photos of fracture surface of PLA blends with various composition of natural fiber. From the photos, it reveals that the fibers are not in loose form but in a bundles form which is embedded in the PLA matrix. The photo also shows bundles of fiber protruded from the matrix in 90-10% and 70-30% blends, and we can see the track of bundles fibers as shown in the 80-20% blend. The SEM photos also reveal the difference in size of bundles fiber. We can clearly see in 70-30% blend has the largest size of fiber bundles compared to the other compositions. As for 80-20% and 50-50% blends have nearly the same size of bundle fiber. For the 50-50% blend shows the fibers was not well distributed in the PLA matrix, which forms a void at the surface when stress is applied. Next, the SEM photos of PLA blend with various amount of graphene with the addition of Ultra Plus TP01, which act as a compatibilizer. The compatibilizer has a fixed amount of 0.5 weight% for each composition, which is shown in the formula table earlier. We can see at the 0.25 weight% of graphene blend shows the dispersion of graphene coated with the compatibilizer throughout the smooth surface of PLA matrix. However, in the case of 0.5 and 0.7% of graphene blends, reveals the distribution of graphene which form an irregular shaped granule throughout the matrix. On top of that, PLA blend surface become rough due to filling effect of this granule-shaped graphene in the blends. The void and granule-shaped graphene indicate that there is no interaction between PLA and graphene for the 0.5 and 0.75% blends. Lastly, in conclusion, the objective 1, which is to analyze the tensile strength of PLA additive materials such as natural fiber and nanographene, was successfully carried out. However, the result data out of the two compositions, the PLA fiber composition was shown to have the most promising tensile strength. For the objective 2, which is to identify the morphology of fracture surface morphology of tensile break specimen for each composition, SEM of tensile fracture surface of PLA fiber indicate poor adhesion of the filler tube matrix. On the contrary, the incorporation of TP01 improved the interfacial interaction and adhesion between PLA and graphene. However, the dispersion of fiber in 70-30% shows that the fibers forms a bundle in some areas, which results to drop in strength. Lastly, the objective 3, which is to study the effect of distribution and adhesion of fiber and nanomaterials in PLA blend toward mechanical strength of each blend, was successful. Hence, the SEM analysis shows that there was an interaction between PLA and graphene, but there was no enough compatibilizer agent to disperse the graphene. Thus, the graphene agglomerate, which affect the strength. And last, the recommendation, adding a few analytical methods such as TGA, AFM, and TEM to support the study. A study of determining the ideal type of natural fiber and nanomaterials in improving the effectiveness of reinforcement of PLA. A preliminary study on the process parameters is required in order to achieve optimum parameters when producing the samples. Particle size analyzer is required to determine the size of each reinforced materials, which will result to a better strength result. Analysis on the combination of PLA fiber and nanomaterials to further enhance the mechanical strength of the blend. That's all from me. Thank you.